Now that you've mastered naming binary compounds that contain type 1 metals, let's look at compounds that contain type 2 metals. Now, this is an interesting statement. Listen closely. All metals that are not type 1 are type 2 metals. These metals, type 2 metals, form cations, or positive ions, that have two or more possible charges or oxidation states. For example, we have copper that forms both a 1 plus and a 2 plus cation, and these are named copper Roman numeral 1 and copper Roman numeral 2 respectively. The Roman numeral in parentheses following the element's name refers to its charge or oxidation state. The iron forms a 2 plus and a 3 plus cation. We call these iron 2 and iron 3. And so we're into a different type of naming now because we're going to have to specify exactly which charge these ions have. So it's a bit more complex than naming with a type 1 metal. But if you go about it systematically, it is not difficult. You just have to be careful. All transition metals, which are groups 3 through 12 on your periodic table, or they may have B designations, 3B, Roman numeral 4B, Roman numeral 5B, and so on. These are all type 2 metals except for zinc, silver, and cadmium, which we spoke about when we talked about type 1 metals. The lanthanide and actinide groups, which are at the bottom of the periodic table, those two 14 element periods that are down at the bottom, or rows, those are also all type 2 metals, meaning they have more than one possible charge. Now, some other very common type 2 metals that we'll deal with quite a lot are Pb, which is lead, Bi, which is bismuth, Sn, which is tin, and Sb, which is antimony. These are also type 2 metals. The only naming difference between binary compounds containing type 1 and type 2 metals is this. The type 2 metal compound must contain a Roman numeral in parentheses following the metal name indicating the charge of the type 2 metal cation. This is important because since these metals have more than one possible charge or oxidation state, when they're written as names instead of formulas, the only way you'll know how many of that metal are in the formula is by the Roman numeral indicating its charge. Let's look at some examples. Here we have CuO. This is Cu represents copper. The O represents the oxide ion. Because the oxide ion is a 2 negative charge ion, the copper combined with it must be 2 plus for this to remain a neutral compound. So it's copper 2 oxide. Next we have Cu2O. Here the oxide again is a 2 negative ion because it requires 2 coppers to balance that 2 negative charge. Each copper must be 1 plus, so this is copper 1 oxide. Next we have iron 3 nitride. The nitride ion is 3 negative, so the iron here has to be 3 plus in order to balance that 3 negative charge, so we have iron 3 nitride. Next we have Fe3N2. Here the nitride ion again is 3 negative. There are 2 of them, so 2 times 3 negative is 6 negative. It needs 6 positive charges from the iron to balance it. There are 3 irons, so 3 times 2 plus is equal to 6 plus, which would balance those 6 negative charges. So the iron here is 2 plus, and the name then is iron Roman numeral 2 nitride, and we just call that iron 2 nitride. Next we have CoCl3. Each chloride is 1 negative. There are 3 of them, so the cobalt has to be 3 plus in charge to balance those 3 negative charges. And then finally we have CoCl2, where we have 2 chlorides, 1 negative charges, so the cobalt here must be 2 plus in charge. Again, the key to these is to look at the anion, because the anion charge will always be consistent. Once you know the anion charge, you can then figure out what the charge on the cation or the positive ion is from that. Here's an important note. The Roman numeral in these names indicates the charge on the type 2 metal cation. It does not in any way refer or imply the number of anions or cations in the formula. Please remember that Roman numeral refers only to the charge on the type 2 metal that precedes it. It does not tell you the number of that type 2 metal or the number of the negative ion or anion that are combined with that. It is simply the charge. Naming binary compounds that contain type 2 metals has a little bit of an edge to it, and the edge is that you must determine the charge based on the anion that it's combined with. So the anion charge is always consistent. Let's look at an example, Fe2O3. So the example we're working with is Fe2O3. What we're going to do first is write the symbol for both ions, the charge for the anion, and then we'll make the subscripts coefficients with the symbols. So we're continuing to use Fe2O3 as our example. We brought the subscript up as coefficients, so we have 2 Fe, and I put an X plus there because we're not sure of that charge yet, is what we're going to determine, and we have 3 O2 negatives. So there are a total of 6 negative charges represented by the 3 oxide ions. That coefficient 3 times the 2 negative. 3 times 2 negative is 6 negative. Since there are 2 FeX plus cations, the charge on the iron cation must be 3 plus, because 2 times 3 plus would equal 6 plus. 6 plus charges will balance the 6 negative charges from the 3 oxides. So when we go to write this formula, we would write it as iron, Roman numeral 3, representing the charge on the iron oxide. So iron 3 oxide. Based on what we've learned so far, let's look at the following formulas and write the name from the formula. Now each of these formulas, I'll give you a hint, are type 2 metals, so you'll need to find the charge on the type 2 metal by looking at the anion, similar to what we did with Fe2O3, and then go ahead and write its compound name. What I'd like you to do is to pause the podcast, complete these, and then when you resume the podcast, the answers will be waiting for you to compare to. Welcome back. Let's compare your answers to mine. First of all, we have tin Roman numeral 2 oxide, or tin 2 oxide. The oxide ion is 2 negative. There's 1 tin with that 1 oxide ion, so the tin has to be a 2 plus charge. Thus the Roman numeral 2 representing the charge on the tin. The nitride ion in Pb3N4 has a 3 negative charge. There are 4 of those, so 4 times 3 negative is 12 negative. There are 3 leads there. So if you take that 12 negative and divide by 3, each of the leads would need to be a 4 plus charge in order to balance the 3 negative charges on the nitride ion. So that is lead, Roman numeral 4 nitride, or lead 4 nitride. For the CuBr2, each bromide is a 1 negative charge. There are 2 of those, so the copper must be 2 plus to balance. In UF6, each fluoride is 1 negative, so the uranium here is a 6 plus charge, so uranium 6 fluoride. FeP, the phosphide ion, is 3 negative. The iron, because they're 1 to 1 here, the iron must be 3 plus in order to balance that. And finally, TiO2, each oxide ion is 2 negative. There's 1 titanium to balance it, so the titanium must be 4 plus in order to balance the 4 negative charges, so it's titanium 4 oxide. So far we've talked about binary compounds that contain nonmetals only, which are binary molecular compounds. We've also talked about 2 types of binary compounds that contain metals, the type 1 metal binary compounds and the type 2 metal binary compounds. There's another classification that we need to deal with, and these are inorganic compounds that contain more than 2 different elements, and we're going to say usually this means they contain a polyatomic ion. For our purposes, they contain a polyatomic ion. Now, a polyatomic ion is a charged molecule in which atoms within the molecule share covalent bonds. The polyatomic ion is then bonded to a type 1 metal or a type 2 metal, or possibly to a positively charged polyatomic ion. Almost all polyatomic ions are negatively charged. There are just a few that are positively charged. So normally when we talk about polyatomic ions, we're talking about polyatomic anions rather than cations. But there are a couple, and we'll learn them. So you have to know the exceptions, and it makes life easier when you do. The next 5 slides are going to contain common polyatomic ions. These polyatomic ions should be memorized. It's the best way to deal with them. So I'm going to recommend that you pause the podcast at each slide and just write these down, the formula and charge and the polyatomic ion name. These would be good to make 3x5 cards out of, with the ion name on one side and the formula and charge on the other, and practice naming these, practice writing the formula and charge for these. It'd be very helpful to you as you go on in chemistry, because these will affect you in many areas, and not only in naming inorganic compounds, but also when we talk about naming acids, which will be on the next podcast. One thing you'll notice as you're looking at these slides containing these common polyatomic ions is that so far all the ones that I've shown you have an ATE ending or an ITE ending. One of the things you'll also notice, for instance, when you look at this slide, we have perchlorate, which is ClO4 minus, chlorate, which is ClO3 1 minus, chlorite, which is ClO2 1 minus, and hypochlorite, which is ClO minus. All of these chlorine-based polyatomic ions have a 1 negative charge. The one that we can look at as a base for this is the ClO3 minus. The ATE ion we can look at as a base. If it has one more oxygen than the base ion of ClO3 minus, we put a per prefix on it, perchlorate ClO4 minus. If it has one less, we change the AT ending to an IT ending. So ClO2 minus is chlorite. If it has 2 less oxygens than the base of chlorate, ClO minus, we put a hypo in front of it, so it's hypochlorite. So that's another way you can look at naming these, but really memorization seems to work best for most people. So continue to pause as needed, write these down, make your cards, and take some time to memorize these. We are continuing to look at slides with common polyatomic ion names and their corresponding formula and charges. Again, so far we're still looking at the ATE, ITE ending polyatomic ions. Monoatomic anions, or negative ions, always end in IDE. Almost all polyatomic anions end in ATE or ITE endings, with a few exceptions, and I have a slide toward the end that gives you a few of those exceptions. But keep in mind, when you hear a name of a compound that has an ATE or ITE ending, it will always have a polyatomic ion involved. Of special interest on this slide is the positively charged ion at the bottom, polyatomic cation, which is called the ammonium ion, and H4 with a 1+ charge is the ammonium ion. Here's the final slide that contains common polyatomic ions. Notice here also are the first polyatomic ions that will have an IDE ending. There aren't many that do, but you have to be aware of these because they're useful, and the one hydroxide especially is very common. So we have the cyanide ion, Cn-, the peroxide ion, which is 2 oxygens combined with an overall 2 negative charge. Remember, the oxide ion is O2 negative, the peroxide is O2 2 negative. You'll want to keep those straight. The hydroxide ion is OH negative, and we also have another polyatomic cation. This is the mercury 1 ion, and it's two mercury 1 ions that are covalently bonded together, Hg2, 2 plus. Okay, so it's Hg2 with an overall 2 plus charge, which means there's a 1 plus charge or oxidation state for each mercury. This is the end of part 3 of the video podcast series having to do with naming inorganic compounds. I want to leave you with a quote from C.S. Lewis. Even in literature and art, no man who bothers about originality will ever be original. Whereas if you simply try to tell the truth without caring 2 pence how often it has been told before, you will, 9 times out of 10, become original without ever having noticed it. I wish you well. Stay tuned for part 4.